Hello, you should hear me and see the desktop. Does that seem okay right now?
Hello.
Yes.
Okay, thanks. All right, so everything seems okay?
Yep.
Then, okay, so what we're gonna do today is we're gonna start chapter 3 in the book. Talk more, talk about grammars more. Okay, and as we go along, we'll keep filling in details about more and more about grammars. So here is, where is it? Here's the summary of chapter 3. Okay, and chapter 3 works on a series of grammars: grammar 1, grammar 2, grammar 3. And I wrote the grammars out on a piece, on a text document, to have them all in one place. So here's the grammars: 1, 2, 3, and 4, 5, and 6. So we'll see how far we can get through these grammars today, and see what they're trying to do. So we want to start understand. This is a sequence of grammars that are trying to solve a problem. Okay, so the problem is how to, and the problem is how you describe arithmetic. Okay, so what do we mean by arithmetic? I mean, you all know how to write things like 3 times 4 plus 5, and you kind of know what that means. And you can use variables, so you can say x plus 4 minus 5 times y. You can mix it. So we have this notion of arithmetic, but there's actually, this is a language. There's a grammar to this. There's a grammar that says, for example, that that's not an arithmetic expression. That doesn't make sense. That's not an arithmetic expression because it's got an unbalanced parentheses. For example, it makes a difference whether you close it there or if you close it there. But that by itself is grammatically incorrect. It's also incorrect to write something like x plus that doesn't make sense either. The parentheses are kind of backwards. So there are grammar rules that describe how you should write arithmetic expressions, but then there's something much more subtle than that. Three uh, you don't read these quite the same. These things aren't read from left to right. Like this one says you should do that first. The order of operations is you should do that one first. Here you should do that one first. Okay. Now we're going to see that that means that these things have two different tree structures. This one, from our point of view, this one is a tree that says that you're taking the sum of 3 with something else. What you're taking is the sum of 3 with the product of 4 and 5. Okay. Whereas this other one is a tree that is the product, because you do the multiplication first. So it's the, I'm sorry, it's the sum of, now on the left is the product, and this is a 5 over here, and then this is the product of 3 and 4. We really want to get at how do we make sure that this becomes this tree in a programming language. When this thing gets parsed, we want this thing to parse into that tree, but we want this one to parse into that tree. So when we understand how programming languages work, the programming languages are going to take these arithmetic expressions and make trees out of them. Then this is the sum of 3 with something. So first you have to do that something. 4 times 5 is 20. So this is the sum of 3 and 20. That's a post-order traversal of this tree. This is the sum of two things. Well, the thing on the left is that product of two things. So you need the 3 times 4 is 12. then you're going to take the sum of 12 and 5 and get 17. Okay. So you don't just, like this one did get read from left to right, do the 3 times 4 first, but this one got read from right to left, do the 4 times 5 first, and then do the sum. We want to get at the grammar rules that guarantee that these things have the right order of operations. Another way to put this is it has the right precedence. Multiplication has higher precedence than addition. It gets done first. Multiplication has higher precedence than addition. Okay, so these grammars over here that are trying to build that system up. They're trying to build it so that when we have the right grammar for arithmetic, these grammars describe languages that are kind of like arithmetic. When we have the right grammar for arithmetic, we will know that that's not legitimate, and we'll know that this thing means this, and this one means this, that the meaning of it is this. You're not supposed to do 3 times 4 is, like here, you're not supposed to do 3 plus 4 is 7, then 7 times 5 is 35. You're not supposed to do that. Now, if you want that, yeah, then you can do parentheses, 3 plus 4 times 5. So we want our language to allow us to put parentheses, because then this becomes the tree, this becomes the product of, on the left is the plus, and on the right is the 5, and it's the sum of 3 and 4. Okay. Notice the tree looks, yeah, the tree looks similar to this one, but this one's got plus here, and this one's got my product here, this one's got times here, this one's got sum here. Okay, so yeah, we want this to be in our language, and we want our programming language, when it builds the tree for this, to end up with this tree. It should come up with that tree for that expression. Okay, these trees here, can't remember, these are called abstract syntax trees. They're also called expression trees. So they're called abstract syntax trees or expression trees. Okay, so this guy's got that one. Okay, this one has that abstract syntax tree. This expression has that abstract syntax tree. We want a grammar for arithmetic that tells us that turns arithmetic expression, well, does 2 things. It'll tell us what are legitimate arithmetic expressions and what are illegitimate arithmetic expressions. But more importantly, it'll tell us what the structure of an arithmetic expression is, so that we will get an automatic system that goes from this to this structure. And arithmetic is a good way to study this, because arithmetic is actually fairly complicated. Once you understand how to do this for arithmetic, it's real easy to describe how to do this for things like if statements. Yeah, this has got a tree structure too. I think we mentioned before, this has got a tree structure too, and there'll be a grammar for our programming language that gives this a tree structure that would look something like, it's an if statement with 3 branches. Okay, it's an if statement with 3 branches because an if statement has 3 parts to it. Okay, and the left part is this equality operator with X on the right and Y on the left. And then this branch is just a print with 1 subtree, which is you're printing X. And the last branch is also print, printing y. All statements in programming languages will turn into these abstract syntax trees. That's what a compiler does. That's what an interpreter does. It takes statements in your language and turns them into abstract syntax trees. And then you walk the tree. So an if statement says, do this part first. If it returns true, do that part. But if it returns false, do that other part and skip this part. Okay. You don't skip parts of an arithmetic tree. An arithmetic tree, you do everything in it. But an if tree will be, the whole point of an if tree is that you skip one of the branches of the tree. There's 3 branches, and depending on whether the first branch is true or false, you either do the second branch or do the third branch and skip one of them. Okay. It's easy to write compilers and interpreters that work with these trees. Yeah. That's how all compilers and interpreters work. They take statements in your language and turn them into trees, and the grammar is what directs the conversion from this to this. It's the grammar that lies at the heart of how to go from this string. One way to think about it is these are all strings, and this is a tree data structure. So here, that's a string, and then that's a tree data structure. So this is a string. So we want to convert strings to tree data structures. Okay. And this is a very important way to understand programming languages. The parser takes a string, uses your grammar to convert the string into a tree data structure. The parser takes the string, uses the grammar to convert it to a tree data structure, an abstract syntax tree. You start with a string in your language. The parser turns it into an abstract syntax tree. That's the first step of a compiler. Then the second step is to compile the tree into machine code, or if it's an interpreter, just to execute this, just to walk the tree, traverse the tree, and do what the tree says. If says, go over here, figure out this, equal says, figure out these are the same. If the answer is true, then if says, go do this. But if this comes out false, if says, go do that. Okay. So that's where we want to. Now, once the hardest part is the surprisingly enough, the arithmetic part of it is one of the trickiest parts of all this. Getting arithmetic right is kind of difficult. So if we understand how to get arithmetic right, it's pretty easy to get most of this other stuff right. Okay. So the textbook emphasizes, and almost all textbooks do this, they emphasize what a grammar would look like for arithmetic, because it's very instructive of almost everything you need to know about grammars is buried already in the arithmetic idea. Okay. All right. So now here's the starting point is these 3 grammars are in the first page of the chapter. None of them are good grammars. These are good, are bad, and we want to see what they kind of do. And then after these 3, there's going to be a sequence of grammars that's trying to get to the right grammar. Okay, so then there'll be 4, 5, and 6 are getting closer to the right grammar for arithmetic. Okay, now let's start with these first one. Let's start with these first 3 and see what they do. So I'm going to just copy this and put it in a window by itself. And we want to look at what these 3 grammars do. Okay, now there's 2 ways to think about a grammar. One way is the grammar tells you how to write sentences. And then the other way around is if I have a sentence, the grammar tells me how to build a tree from it, how to parse it. So let's do the first step first. What does a sentence look like in this? Okay, well, a sentence is called sub-expression. And a sub-expression is either an A, a B, a C, or a subtraction of 2 sub-expressions. So a sub-expression gives me, I'll pick the sub-expression minus sub-expression. Okay, now what does that give me? Well, now I can do the same thing. I can take this one and start back over here on the left. That can give me a B. Okay, so this one will give me a B, and I'm still left with minus sub-expression. Okay, but sub-expression, now that, then I can say what sub-expression is. Well, the thing is, that's B minus, I'll go ahead and do the same thing over again. I'll use this one again. Okay, and then, well, what can that give me? Yeah, so I got the B minus, and then I'll turn this sub-expression into a C, and I'm still left with the other sub-expression. Now, if I want, I could turn it into another one of these and keep building up a longer and longer chain, or I could just say it gives me a B minus C minus A. Now, I'll stop there because these things don't go anymore. Okay, so what this thing builds up is chains of subtractions. Okay, so it builds, and there's no addition or multiplication, it just builds up chains of subtractions of the letters A, B, and C. Yeah, so it gives you, in general, expressions like A minus B. Oops. It gives you things like A minus B, or B minus C, or A minus C minus B minus A, things like that. Okay, so that's what G1 does. What about G2? Let's just play around real quick with G2. G2, we start with sub-expression. So what we did here was a G1 example. We did a G1 example. Okay, let's try a G2 example. The thing is that this is going to turn out to be the same. We get the exact same thing from G2. Okay, it's not going to be any different. So watch. I start G2. I start with the start symbol, and I ask, what does it expand into? Well, I can expand it into a variable, or I expand it into that. So I'll expand it into this one. It's a little bit more interesting. Okay, then what does that expand into? Well, I don't have any choice about this one. It has to become either A, B, or C. So I'll make it B. And then I've got this sub-expression. Okay, right? So now what can this expand into? Well, this can expand into either this or a variable. I'll go ahead and expand it into this again. So now this will expand into, there's the B minus, okay? But now when I expand that, I don't have much choice here. I have to put a variable there. So if I go one more, if I keep expanding this, I'm going to have a B. Then I don't have much choice here. I have to put a variable here, okay? And then there's the sub-expression, okay? And then I can expand this thing at whatever I want, and B minus C minus, and then I'll go ahead and expand it into a var this time. See, I'll go ahead and expand that one into a var, and then I get the same thing, B minus C minus A. Notice that I ended up with the same string as I did before, but with a different derivation. Okay. All right. And if you play around with it, you'll see that you can't generate anything different with G2 than you can with G1. It's still going to give you letter minus. Well, then this thing will turn either into a letter or a letter minus. Okay. And if you do G3, if you do a G3 example, it's very similar to G2. If you start with this, okay, well, G3 would give me, if that's the more interesting case, unless I just want one single variable, I have to start with this to get something more interesting. Okay. Now, let's see. What can I expand this one into? I can expand that one into this thing again. So I'll expand that into that thing again. Then there's still the minus var here. Okay. So I expanded this one into another one of these. Okay. Okay. Now, what can I expand? No, I'm doing left derivation. So I'm always expanding the thing on the left. So now what can this thing expand to? Well, this thing can expand to, I'm going to switch to var this time. So this is going to give me var, and then I'm left with minus var, and I'm left with minus var. Okay. Now, var can give me b, and I'm going to do this the correct way. I do one step at a time. So that's b minus var var, and then that'll give me b minus c minus var, and then finally I'll get to b minus c minus a. So I've derived the same thing, but with the G3. And if you play around with it, G1, G2, and G3 always give you the exact same expressions. You can't get anything but these out of either G1, G2, or G3. Okay, G1, G2, and G3 all give you the same things. But if I think of this derivation, each of these derivations is giving a tree structure to this thing. See, each one of these derivations gives a different tree structure to this. So let's draw the tree that each one of these is doing. So in between here, I'll put the tree that this one is. Okay, at the root of the tree is this guy. Okay, so the root of the tree is that. Then it expanded to a left branch and a right branch. So expanded to a left branch and a right branch, and the left branch and right branch for each one of these things. Okay. Now, that left branch expanded to just a B. So the left branch was just a B. But the right branch expanded to, I'm sorry, I forgot the minus signs. There's actually, when this thing expanded, it was subbranch minus, so I have to put there's the minus sign. Okay, so it's B minus then this sub-expression. Okay, so there's sub-expression gave me a sub-expression minus sub-expression. So it branched into three things. Okay, this one just gave me the B. Then this one branched into three again. Okay, so this one is going to branch into three again. It's going to have its left branch, its center branch, and its right branch. Okay, the left branch is sub-expression. The middle branch is the minus sign, and the right branch is another sub-expression. And then these guys this one gave me the letter C, and this one gave me the letter A. Oops. Okay, that's the tree for that one. That's the parse tree that went with this derivation. This guy expanded into three branches below him. So there they are. Then this left one expanded to B. So the left one expanded to B. The right one expanded to, see, from this right one, we just copied it here, but then that right one branched into that. So that's this one branching into 3, okay? And then this one became the C, and this one became the A, okay? Now, what about this tree? Yeah, now let's do one more. Let's do the tree for this one. It's going to be a different tree, okay? Okay, the tree for this one will be, well, we start with the start symbol, that's at the root. There's the start symbol at the root. It branched into 3 ways like this. Okay, so it's got a 3-way branch. Okay, and we've got there on the left branch, a minus sign on the middle branch, and a copy of sub-expression on the right branch. Okay, now there just became the letter C, no, letter B. Okay, minus sign stays minus sign. What did this thing expand to? This guy expanded to that thing there. This one expanded into 3 branches, a there, a minus sign, and another sub-expression. So this is the there. This is the minus sign, and then this one's another sub-expression. Okay. In this case, this there gave us this there became the C. Okay. Then this one expanded to just there. We went up here and we've said sub-expression is a there. So this one now expands just to, oops, there. And then there gives us the A. Okay. So get a very different shaped tree. Now, the tree, just like we saw a while ago, the tree represents grouping. See how the tree says that's grouped there? On your hand, this tree says this is grouped there. See, lower branches represent grouping. So we can think of this thing as having grouped our, we can think of this as having grouped our expression, okay? So see this expression here? This tree is basically saying that this is grouped, I'll put it below. It's grouped like this. B minus, then the C minus A are grouped together. Because see, they're lower in the tree. So this subtraction is grouped on the right. Okay, all right. Now, this one gave us the same grouping. Okay, it's got a different tree, but notice it's still grouped. It's still grouped this on the right. Okay, now what about this one? Let's go ahead. If we do this one, I think we'll see that this one's going to group differently. Well, let's see. Okay, let's go ahead and let's build a tree for this one. It's worth doing. Okay, there's the root. The root broke down into the left branch, middle branch, right branch. The left branch is sub-expression. The middle branch is the minus sign. And then we have there over here. Okay, that there is eventually the one that's over here on the right, over here on the right. That there gives us the A. Okay. This sub-expression branched into there minus there, sub-expression minus there. So this one branched into 3. Okay, and it gave us sub-expression on the left, okay, minus, and then here was the there. Okay, that there gave us the C. Okay, and then this left sub-expression, it's the one that expanded eventually to just, let's see. So this one expanded to that. Okay, that's this one over here. Then this one expanded to just there. So this one's going to expand just to there now. And that there is going to give us the B. Okay. Now, how did this thing group things? Notice it grouped it the other way. See, this one grouped on the left. So this one actually grouped it as B minus C minus A. Okay. So the grammars change the way things get grouped. By writing the grammar this way, you're actually grouping things on the left. When you write the grammar this way, you're grouping things on the right. This grammar actually doesn't group things left or right. With this grammar, we could actually take this string and give it more than one parse. So with this grammar, I could have given the same expression multiple parses, and I could either put it on, I could have grouped it on the left or grouped it on the right. I could use this grammar to group on either the left or on the right. See, now the way you read it, it says that a sub-expression is a subtraction of two sub-expressions. So if you look at this guy, you could think of that sub-expression as the one on the left, or you could think of that as the one on the right. So you could think of this as either this one on the left, or you could think of this as this one on the right. So the grammar is ambiguous and it lets you group either way. But then look at this expression, this grammar. When you get to that grammar and you have this expression B minus C minus A, the first thing in it has to be a variable. Okay, so you're forced in grammar 2 to put the B by itself. So you're kind of forced to say that it's a letter minus the sub-expression. So you have to say a variable minus sub-expression. You don't have any choice because, see, this one limits you on the left. It says you've got to start out by either giving me just one letter or one letter followed by a sub-expression. So you're forced to put the B by itself, then this is the sub-expression. So grammar 2 groups things on the right. Grammar 3 does it the other way around. With grammar 3, you start with this thing, and you've got to put the variable on the right end. Okay, so you have this expression B minus C minus A. In this grammar, if you've got something that's more complicated than one variable by itself, when you use this part, it's saying it's got to be a variable on the end and then the sub-expression. So you've got to make this guy the there by itself. There's the sub-expression. So grammar 3 groups on the left. So grammar 3 is what we say left associative. It's going to force you to group on the left, even if you wrote with no parentheses. Yeah, if you have something like A minus B minus C, this grammar is going to group it on the left. It's going to force these two to be grouped together. Okay? This grammar is right associative. It forces you to put the did I do that right? Yeah, it forces you to put the sub-expression on the right. So if you have something like A minus B minus C, you're forced to make the A the variable, and you're forced then to group these guys on the right. Notice there's no parentheses. None of these languages have parentheses. The grouping is forced by way you parse, according to this grammar. Notice that's really interesting. The grouping is forced on you by the structure of the grammar. Okay, that's where the name of this chapter comes in, where semantics meets syntax, or syntax meets semantics. This is the syntax, but the grammar is forcing me to say something about what it means. It means do that operation first, then do that operation next. Whereas this one down here, with the same syntax, see, this grammar here on this piece of syntax makes this guy the first operation and then does this one last. This grammar with the same expression makes this the first operation and leaves this one left because it's left associative because of the way it forces things on you. Okay, that's what's real interesting, is that you can change the structure of your expression by rewriting your grammar. This one is neither left associative nor right associative. This one doesn't say how you should group. It's ambiguous. If you give this grammar A minus B minus C, you don't really know which operation to do first. The grammar is not helping you. Programming languages never want grammars like these because they don't tell you what's the right tree for that expression. I built one tree here, but I could build another tree. With that grammar G1, I could build a second tree for that same expression. You can do that yourself. Just essentially just flip this tree over a little bit. Okay, but you have to change the steps of the derivation. You change the steps of the derivation a little bit. You instead of expanding this one into the letter, you expand this one into this and expand this one into the letter A. So instead of expanding this one into B and then expanding this one into a subtraction, expand this one into the letter A and make this one into the subtraction, and then it'll group it the other way. It'll take that same expression, A minus B minus C, and group it the other way using that grammar. So that grammar is not going to tell you how to group your expressions, okay? But the other two grammars do. The other two grammars, let me save this. The other two grammars have some kind of, the way they're defined, one manages to be right associative and one manages to be left associative. Okay, right. So we want to build on this idea. So we get a hint here of what's going on. Okay, we can build associativity into an operator by writing the grammar carefully. Okay, here's an operator and it's neither left nor right associative. Here the operator is right associative. Here it's left associative. Oh, and in the arithmetic we use, left associative is the right one. You're taught that if you see this in math, you do it from left to right. If the operators have the same precedent, you're supposed to do it from left to right. So this is actually the right grammar from our point of view. That's what we use in arithmetic. Though there are some operators in programming languages that are right associative that would use this grammar, the arithmetic operators would use this grammar. They're left associative. Okay. Arithmetic operators, the same thing is true with multiplication, addition, multiplication, subtraction, division, are all done from left to right. Oh, let me give you an example of a right associative operator. Here's a real famous example of an operator that is right associative. If you do this in most programming languages, if you say A equals B equals C equals D, you're allowed to do that. I mean, you can do that in JavaScript and you can do it in Java. Okay. How's that grouped? You don't read that. You can't read that from left to right, because if you read it from, like if I go here and say that D equals 4, C equals 3, B equals 2, okay? I can't read this from left to right. If I read it from left to right, I would be saying that A is 2, and then B is 3, and then C is 4, and I'd end up with the variables being different. It wouldn't make any sense. I don't do this from left to right. I do it from right to left. What this is, if it's grouped from right to left, it's A equals the grouping of B equals the grouping of C equals D. Then close that one, close that one, okay? Oops, okay? So it's done from right to left. Equality operator is right associative. The equality operator is a good example of a right associative operator because it doesn't make sense to read this one from left to right. It makes sense to say C is, oh, I have to give you what D is. Okay. So now C is going to be made 1, then B is going to be made 1, and then A is going to be made 1. So all the variables will end up being A, B, C, and D. They'll all be equal to 1. Okay. So
you have D twice.
Pardon me?
You have D twice. You have D equal 4 and D equal 1.
Oh, this would oh, I did read it from yeah, I'm sorry. So this would be D is 4, so then C becomes 4, then B becomes 4. So everything ends up being, they all end up equal 4. Yeah. So D, C, B, A. So 4, then C becomes 4, then B equals 4, then A equals 4. Again, if you read it from left to right, it wouldn't make sense. They wouldn't end up being all equal because you would have A equal B. So A would get 2, then B would get 3, then C would get 4. Yeah, and then they would not be equal to each other. That would kind of defy what you thought that should mean. Okay, so addition, subtraction, multiplication, and division are left associative, and equality is right associative. Here's an interesting one. What's x less than y less than z? How's that treated? Is it x less than y less than z, or is it x less than y less than z?
It's look like it's the same.
Are they?
I said it's look the same for me.
Okay, analyze it. What does that return? Can it return 57.8? Can it return 1,227? What does it return?
You're saying it's just a Boolean?
Well, yeah, it returns a Boolean. It's a Boolean operator. So it returns what?
True or false?
True or false? Can you put true or false on the left-hand side of a less than symbol?
Nope.
Nope. This doesn't make sense. And this doesn't make sense. The less than operator is not associative. You can't write this. It won't parse. It's not associative. Notice we have 3 kinds of operators: left associative, right associative, and not associative. Eventually, we'll see that you can write a grammar in a very specific way to make an operator not associative. That won't parse. That has no meaning. Now, you've seen that before. In math, it means that y is between x and z. But Java doesn't allow this. Java, C++, and C, and JavaScript, they don't allow you to write that. In a math book, you can write things like x is between 0 and 1. But how are you supposed to write that in Java? If that's what you want, what do you actually write? If you see that in the math book and you're told translate that into Java, how do you do it?
Two separate statements.
What are the two separate statements? Actually, you write one state. No, you shouldn't say it that way. You write one statement. What is it?
It's 0 less than x and 0 and
Yes,
x less than 1.
you write two expressions, but connect them with the and operator. So that's still one expression. It's just a more complicated expression. You write x is greater than 0 and x is less than 1, which is how you read this anyway. You read this as x is greater than 0 and x is less than 1. The less than operator is not associative. So Java will not allow that. So you have to turn that into its more verbose, which is what it means in the math anyway. It means x is positive and x is less than 1. Okay, so this one doesn't group in any way at all. It's not associative. And you can see why. It's because if you grouped it this way, you'd get a Boolean, and you can't compare a Boolean to a variable, a value, like an integer. You can't compare Boolean with number. You can't compare number with Boolean. Okay, so this is an example of a non-associative operator. Okay, so some operators are right associative and some operators are left associative and some operators are not associative. Now, if you go to look this up, here's a nice table. There's all the operators that Java has. There's all of them. And for every operator, you're taught what its level of precedence is and whether it's associative or not. Notice that some of them are not associative. So like the plus plus operator is not associative. Another example that's not associative are the relational operators. They're not associative. Okay. Most of them are either left to right, which is another way of saying left associative, or they're right to left. See, now the equality operator, where is it? Okay, here's the equality operator. See, it's right to left. See, we said the equality operator, you read the equality operator from right to left, which is the same way of saying right associative. You're grouping things on the right. So right there, they tell you that the assignment operator is right to left. On the other hand, an arithmetic operator, see, all the arithmetic operators are left to right. They group on the left. Arithmetic operators should group on the left, okay, which we said was the G3. G3 group things on the left. G3 group things on the left. See, left means push lower. Grouping on the left means the left gets pushed lower in the tree. The tree is this of this group. So the root has the group on its left. The group is on the left of the root. Okay, so it's real important to see how trees express this grouping. Okay, and then the operators that are non-associative, they won't part. You'll get a grammar error when you write that. Okay, another example was x plus 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 plus. Okay, you can't do the plus plus of the plus plus. Okay, there is no associativity to that. The plus plus operators can only be done one time at one. You can only do that. You can't do That doesn't make any sense. Okay, so there's no grouping of the plus plus operator. So that was over here that the plus plus operators are, let's see, not associative. Oh, the pre-increment is, the post increment is not associative. The pre-increment one, they say right to left. I wonder, I'd have to think a little bit about how that one works. I've never thought of using the pre-increment operator as a right associative operator. I'd have to think about that one. I think what that's saying is that you can do this. I never try that. I think that's what they're saying, you can do that. But what you're not allowed to do is this. How do we know if these things work? How do we know if these things work? How do you find out if something works in Java? How do we find out for sure if that's a legitimate piece of Java or not?
Test it.
Test it. How?
Java Visualizer.
Yeah, Java Visualizer is the easiest way. Otherwise, you have to write a Java program and compile it. So let's go ahead. Yeah, let's try it. Let's take these and go to the Java Visualizer. That's one of the great things about the Java Visualizer. It lets you test things. Okay, so let's create an int x equal 1 variable, and then see if these guys compile. Let's just see first if they compile. If I want, I can say, make it say int y equal that, and int z equal that. Okay. Okay. Yeah, I don't know what they mean. See, it doesn't work. And the other one doesn't work either. See, you can't increment something that's not a variable. So you have to increment a variable. You can't increment something that's not a variable. Here we're trying to increment the result of an increment. So we're trying to increment an integer. See, this thing results in an integer, and this is trying to increment an integer. So it's the same thing as if you try to do something like this. That won't work either. So you can't increment an integer. So I don't really know what they're saying here when they say that the unary pre-increment operator is right to left. I wonder if somebody ever explained that somewhere I can Stack Overflow. I don't know what they mean by that. Yeah, this makes sense to me that the post increment operator is not associative, but I don't know how you could actually do this in any kind of way where you would read it from right to left, because you can't chain these increment operators. So I'm not sure what they're saying when they say that this thing is right associative. Have to think about that a little bit. Maybe I can, yeah, there's probably something interesting there. There's probably some interesting little piece of Java information in this thing right here about the pre-increment operators. Okay. All right. This one makes sense. This is saying something about the unary operator. Okay. That's saying things like, what happens if you take the negation of the negation of the negation of the negation of x? You know, how do you treat that? That's read from right to left. that's negate X, then negate the negation of X, then negate the negation of X. You do that from right to left. So the unary operator should be right to left. That makes sense. It doesn't make sense to start over here and say I'm going to negate something. It makes more sense. Start here, negate X, then negate the negation of X, then negate the negation of the X. So that's grouped right associative. Do that one, then that one. Yeah. So work your way from right to left. Okay. So if you don't put parentheses, it'll end up giving you the more or less the same answer, but it's going to work itself from, it's going to work from right to left. I don't know how you can make sense of this one working from right to left. I say, I don't know what they mean by this one. Okay. But it makes sense for all these other ones. Okay. All right. So we're seeing now that you can use a grammar. All the fact that these things are left to right or right to left or not associative has to do with the way the grammar for Java was written. The grammar for Java was written in a way that made, well, some operators are written to look more like G2, which gives you the right associativity, and some parts of the grammar are written to look more like G3, and none of them are written to look like this. Okay. And then there's a way to write it so that what we don't have here, this is ambiguous, this is left associative, this is right associative. There is a way to write the grammar so that it's not associative. Okay, so that you get this not associativity. We'll see later how you could do that. That's trickier. It's trickier to write the grammar in a way that you prevent somebody from doing this, that you prevent these things from being associative. Okay. All right. Now, the other thing we want to work on is not just associativity, but precedence. See, this has only got one operator, and it doesn't matter. We in all these examples, he just happened to use a minus sign. You could put a plus there, or you could put a multiplication there, or you could put a division. Okay, he just happened to choose subtraction. There's only one operator. What happens when you mix two operators? Okay, when you have two operators, then you have a question of which here with one operator, the question is, do you do things from left to right or from right to left? Once you have two operators, then the question is, which one do you do first? Do you do multiplication first or do you do addition first? Okay, like if I didn't use symbols that you're used to, like if I gave you a programming language that had an @ operator and a £sign operator, which one do you do first? Do you do the 3 @ 4 first? Do you do the 4 £5 first? You know, if you have a programming language with unusual operators in it, and there are plenty like this, there are plenty of languages that could come up with unusual operators. If you have unusual operators, how do you know an expression like that, which one gets done first and which one gets done second? You're used to addition, multiplication, subtraction, division, but if you've got operators that you don't know, or if you mix operators that you do know with operators that you don't know. So if you've got an @ operator and an addition operator, well, yeah, should you do the @ first or should you do the addition first? Which has higher precedence? Okay, if the @ has higher precedence, that means you group it this way. If the £sign has higher precedence, you group it this way. Okay, you can always group, you know, so I can always write that as 3 @ 4. Now I'm saying do the @ first. That might be what the language would do anyway, but here I'm saying I want the @ to be done first because I grouped it. And then I want this to be done later. But I could just as easily group it the other way. I could say 3 @ 4 £5. Now I've said I want it grouped the other way. The precedence rules tell you what it should do when it's no grouping. If there's no grouping, which one of these, which one would you use? Would you group it this way or would you group it this way? That's called the precedence rule. Which operator has higher precedence? if the pound sign, if the @ sign has higher precedence, it really, this guy is equivalent to this guy if the pound sign has higher precedence. This guy is equivalent to this guy if the, I'm sorry, this guy is equivalent to this guy if the @ sign has higher precedence, and this is equivalent to this if the pound sign has higher precedence. So you can always group it whichever way you want, okay? So now the question is, what do grammars do to create that? How do grammars put in precedence, okay? And that's where, okay, now let's look at G4. G4 has 2 operators, okay? So let's look at some examples of using it. So let's look at G4. Let's look at how we might use it. What can an expression expand to using G4? Well, an expression can expand to expression plus expression, or this, or a group thing, or A, B, and C. Let me expand it as expression plus expression, okay? All right, now let me expand that as, well, I'll expand this one as one of these. So I'm expanding this. I'm always expanding the thing on the left. I'm going to expand the thing on the left to that, and that leaves me with exp. And now I'll go ahead and expand everything into a variable. I'll just go ahead now and say exp can be either this, 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 or one of these letters. So I'll expand it to the letter A. And then I'll go ahead and expand. I'll just skip a few steps. I'll expand this one to the letter A. And I'll expand this one to the letter A. Okay. All right. Now, let me do this one again. Let me expand this guy into this one. And then let me expand I'm going to expand this one into A. Okay. Oh, I'm sorry. I wanted to start with the times this time. Okay. So instead of starting with exp plus exp, I'm starting with exp times exp. Then I'm going to expand this one to A. Now I'm going to expand this one to exp plus exp. So the A stays there times exp plus exp. Now A's there times there. And now I'll expand this one to an A plus A. Okay, what have I done? Same thing here and here. But what's different here and here? What's different about these two things?
It's the order of operations.
Yeah, which had higher precedence in that derivation? What's the grouping?
It's left to right.
Let's see. Well, let's draw the tree. Okay, so let's go ahead and draw the tree for this to see how it works. So we started with an exp. See, we started with an exp, and it branched to 3 branches. So the exp branched to left, center, right. The left was an EXP. The left was an EXP, the center is the plus, and the right's an EXP. Okay. What did this guy expand to? He expanded to just the letter A. So he expanded to the letter A. There's the plus. Now this one expanded into the, oh, I'm not sorry, I did that wrong. This one expanded to that. So this one expanded to 3. This one expanded to 3 things: the left branch, a center branch, and a right branch. Okay. Okay. So this one expanded to that. Okay. Then this was A, and then the star, and then the A. And this one expanded to the last A. Okay. So we got, okay. So it grouped this one first. It did it from left to right. Okay. It grouped this one first and left this one second. So it put the star lower in the tree. So it did a left to right grouping. Okay. What about this one? Let's look at its tree. Okay. Same expression. We end up with the same expression, but it's going to EXP, the thing we start with, expands to 3 things: a left, a center, and a right. And in this case, the left just is the A. Okay. The center is the product. Okay. And then the right eventually becomes this thing here. The right becomes okay, this is an EXP. Okay. No, see, I'm sorry. This is a plus of, well, let's see, how I should do it. So the EXP became, oh, I know, I'm doing too many shortcuts. EXP times EXP. Okay, so EXP branched into EXP times EXP. Okay, this EXP becomes the A. Okay, and then there's the times. Then this EXP became those 3 branches. So that EXP became an EXP, a plus, and an EXP. And then this one became that A, and this one became the other A. Okay, now this tree, same expression, put the plus first. It grouped it on the right. So this, now, so what we have is that this is ambiguous, okay? Because the same expression could be grouped this way or this way. So this has 2 operators, addition and multiplication. It's not telling us yet which one has higher precedence, because we were able to group the same expression. We were able to take the expression A plus A times A and group it 2 ways. We grouped it in one derivation, we grouped it with A plus having higher precedence, and the other derivation grouped it with multiplication having higher precedence. So this is not a good grammar yet. It's got 2 operators, but it's not saying yet that one operator has higher precedence than the other. Okay, so it's like our G1, G2, and G3. G1, well, it's like our G1 actually. G1 didn't say if this is a left associative or right associative operator. G2 made it left associative, G3 made it right associative, if I remember right. Okay, so G1 is an ambiguous grammar, and then it got fixed two different ways. G4 is another ambiguous grammar, but with two operators, but it doesn't say whether the plus is higher precedence or the multiplication is higher precedence. It also doesn't say whether they're left or right associative. G4 has actually got several problems. Like if I go back over here to the G4 example, if I work on this one, if I try A plus B plus C, this grammar is going to let me expand that two ways, as left to right or right to left. So this grammar has got multiple problems. This grammar doesn't specify associativity, okay, and it, okay, for either operator, and it doesn't specify precedence, okay. We don't know if this has higher precedence or this has higher precedence. We don't know if this is a left associative operator or if this is a right associative operator. We don't know if this is left or right associative. So this grammar has got two operators and lots of problems, okay? We don't know how to parse this. We don't know how, so we don't know how to parse, we don't know how to parse A times B plus C, because we don't know which is to do first. We don't know how to parse A plus B plus C. We don't know how to parse A times B times C. None of these, you know, do you do this from left to right or right to left? Do you do this from left to right or right to left? Do you do this from left to right or right to left? Oh, I remember, I just thought something. Why did he use subtraction here? There's actually, it was clever of him to use subtraction there. Let me give you a clue. A minus B minus C. Group it this way or group it this way. Think of 1 minus 2 minus 3. Group it this way versus group it this way. What do you get? Group it this way or group it this way. What do you get? Group it this way or group it this way. What do you get? Why did he choose subtraction for G1, G2, and G3? Why did he choose subtraction for G1, G2, through 3 versus addition or multiplication?
Because it changes the answer.
Because it changes the answer. Because it matters here whether you group it this way or this way. What about this one?
Won't matter.
Won't matter. So he purposely chose the operator where it matters whether it's left associative or right associative, to try to get you to realize it could be important. If he'd have used plus there, somebody could have just said, who cares? You're going to get the same answer anyway. So who cares if you use that grammar or that grammar? So he was clever to use the operator where you would care, because you don't get the same answer. If you group it this way, you get a different answer than if you group it this way. Okay. Now for G4, he's using plus instead of multiplication. He's using plus and multiplication. For the left and right associativity, it doesn't matter. But again, he isn't telling you whether to group this way or group this way, though it doesn't really matter. Now, if he did make this subtraction and division, then even the associativity would matter. Okay, because down here, it matters if you write A minus B minus C, or A divided by B divided by C. Those matter whether you group it this way or you group it this way. You don't get the same answer. Subtraction and division are not associative operators. Addition and multiplication are associative operators. Notice I'm using a lot of words. Right associative, left associative, and is associative mean different things. In mathematics, 1 plus 2 plus 3 is left associated. You do that one first. But the addition operator is associative, meaning it doesn't matter if you group this one first or if you group that one first. So addition is left associative, but it's also an associative operator. So it doesn't matter if you group it this way or that way. On the other hand, 1 minus 2 minus 3, you gotta be careful. What we mean here is that in math, you left associate this. You do that one first, then that one. You left associate it, but the subtraction operator is not associative. So that means that if you were to right associate, you would get a different answer. A lot of words going on. So addition is associative, subtraction is not associative, but they're both left associative operators. They're both done from left to right. They're both left associative operators, but addition is associative, so it doesn't matter if you do group it that way or this way. Subtraction is not associative, so it matters if you group it this way or this way. As you learn more about programming languages, these details really matter a lot, especially when you start getting to odd operators. You know, when you do operators that aren't just addition, subtraction, multiplication, and division, all these subtleties about is the operator associative or not, and are we going to make it left associative or make it right associative? Okay, so those kind of issues matter. Addition is associative, subtraction is not associative, but both of them are made left associative. Multiplication is associative, division is not associative, but both of them are made left associative. Okay, so he chose subtraction over here because that was a good choice, because that way the associativity matters. In grammar 4, he's emphasizing precedence here, not associativity, so he went with these two operators. But this grammar does not specify associativity, and it doesn't specify precedence either. Then we'll see, then on Thursday, we'll see how this grammar fixes one of those. That grammar is going to fix the precedence, but not the associativity. And then we'll have to put them all together and fix precedence and associativity. Okay, so we'll have to eventually fix both things, fix the precedence and fix the associativity, and then we'll have a grammar for arithmetic. Okay, so we'll quit there. Okay, so it's actually pretty interesting. You start appreciating this stuff when you start learning new languages and they have operators you've never seen before. When you have to deal with a language that has or if you even just look at Java and you look at some of these operators that you've never maybe like the shift operators, you start realizing, well, should that be left associative or right associative, or should it be, not associative? You start realizing that, when you start seeing more operators in more programming languages, you start appreciating how you need to think about, is that operator inherently associative or not? And should I make it left or right associative? Okay. Remember, subtraction, think hard about this. Subtraction is not associative, but it's left to right. See, that's not the same thing as this saying not associative. Be careful about that. The word not associative here is being used in a different way than saying that subtraction is not associative. In Java, subtraction is left associative, but it's not associative. But this guy is not associative in a different kind of way. Okay? Little details like that give us a language for talking about programming languages that help us understand more complicated things as we go along. Okay, so I think we should stop there. Okay. You have a homework assignment that's due, right? And there'll be another program homework up there pretty soon. And if you have questions about the homework assignment, send me emails or come to office hours, and we'll finish this chapter 3 I think maybe on Thursday, maybe Thursday or next Tuesday, we'll finish talking about how do we build the grammar to fix these problems. Fix the associativity problem and fix the precedence problem. The associativity problem is going to be back to somehow making use of either G2 or G3 mixed in with G4, then mixed, so we're going to mix this G5 with either G2 or G3 to fix G4. Okay, so we'll quit there and we'll meet again on Thursday. And if you have questions, send me email or come to office hours. Okay, so see you Thursday. Bye.